First of all, thank you very much to CyberCamp and to Infibe for giving us the opportunity to be with you this afternoon. This is, an afternoon where there is a football game on. Actually, Spain is losing. And we are here with our workshop. Our workshop is aimed at you having a good time for the next 2 hours. This is the structure of our workshop. We will be giving you an introduction, then we will talk about HPKP, HSTS, and then we will talk about attacks. And first of all, we have to fully understand what those two mechanisms are about. Carmen will dwell on that. We'll go into greater detail, deeper and deeper. And now, after that, we will focus on attacks. And to finish on a good note, we will see real-time attacks that colleagues such as Jose Manuel colleague have developed, and that they are also famous ones. We finish up with a few conclusions, and that will be it. We will introduce ourselves first. My name is Pablo Gonzalez. I am an IT engineer. I work at Telefonica. I also teach in various universities. I am the co-founder of Flu Project and Hackers Club. And I have a number of publications in Godroot, Metasploit, for pen testers, etc. And on my right, we have Carmen Torrano with us. She has a PhD in computer science. She has worked at the SIC for some time. She has a PhD at the University Carlos III, and she's a senior security researcher at 11 Paths. That is to say, Telefonica. And Carmen, you have the floor now. Good afternoon, everyone. Thank you very much for being here, sharing this afternoon with us. And as it's been said already, today we will be talking about two security protocols. So to introduce the topic to you, we will start talking about HTTP and HTTPS. We know that these, as well as SLLs, are protocols that provide security to web browsing. They provide a layer of encryption to the HTTP protocol. However, what does happen with these protocols? Sometimes they have security breaches or security failures or vulnerabilities. And this is the motivation, and this is where the need comes from. That is to say, a need to cover those vulnerabilities and to create protocols to protect that, to shield that. And this is the origin of the protocols HSTS and HPKP. So as you can see here, they are located a layer above TLS and SSL. So, and because we wanted to play with words, we decided to name them the Batman and Robin of web security. They are our superhero. They will help us protect ourselves and to add an additional security layer on TLS and SSL. So therefore, eventually they will help us cover the gap of some of these protocols. We will be breaking them down. We will take a look at the functionalities, and we also will look into the weaknesses, and Pablo will share with you some demos, so that you can also learn how to bypass protocols. Starting off with HPKP, it is the most meaningful, and we decided to start off from here. So one of the main problems of TLS protocol is detecting when there is a replacement in the authorities of the chain of certification. By default, browsers cannot detect a fake certificate, or when any of the nodes in the chain is replaced, and therefore this is what triggers or drives the appearance or the arrival of these protocols. I'm sure that you heard of the problems that we had with the certificates of Komodo. There has been open scandals, so it's a well-known problem. And now let us take a look at how we can solve this problem with HTTP. So we are talking about chains of certificates, and to illustrate it better, this is an example where you can see a digital certificate that we have downloaded, and here on details you can take a look at the tree of certificates. This is the Mozilla one. So we have the root nodes of the CA. HPKP is based on the certificate pinning protocol. Sure, you heard about it before. Certificate pinning help us detect when a trusted chain has been modified, has been changed. So the idea behind certificate pinning is to do a unique matching of a certificate with a unique domain. In this fashion, there is a match, a relationship between the expected pin for the certificates of in a given domain. For instance, if you have a domain.com, where authority of certificate A has issued a certificate, the moment the certification authority sees a difference, when it issues a second certificate for that very same domain, this will help us detect that there is an attempt to issue a certificate by a non-certified authority. And what is HPKP about? This protocol is about public key pinning. That's what it stands for. This protocol, it's specified in the RFC 7469. Final version was released in April 2015, although in early February, in early 2014, there was the draft of this protocol. The draft of this protocol was issued. This protocol allows us to allow a layer of security on top of TLS, and then this help us prevent fake certificates. In case this would happen, it would be possible to detect that through this protocol. So the certificate pinning can be implemented in different ways. In the case of HPKP, this implementation requires to do that client side and also at the level of the server. This protocol allows us to remember the expected pins for the certificate of a given domain. If you know what you are expecting, when you then want to access to this site, what you can do is just to check. You want to check if what you are expecting matches what you are actually visiting. This is basically the idea behind it. So therefore, what happens here is that when you access the server domain, so the certification tree, or at least one of the certificates, should match the ones that we were expecting to visit. So therefore, this helps us detect fake certificates or fraud certificates, and also it allows us to detect a man-in-the-middle attack when someone has stood in the middle of the communication and may have tampered with the certificate or insert fraudulent certificates. If that happens, this will help us detect it. And how does HPKP work? What does the protocol do? Well, basically this protocol works as follows. We have a client, we have a server, and the client sends a request to the server, and then when the server responds, it introduces a headline and then it says, I want to use this header which is public key pins, and in this way we are telling it the certificates and the certification policy wanted to use. We wanted it to use. And this takes us to a situation. What happens in the first connection? What happens the first time this request is made? So when the server sends out the answer, sends out the header, the browser stores that. Therefore, the browser knows the pins that it is expecting for a given domain, and the next time it will log on, it will do the matching. It will compare to those that are expected, those that are waited. But what happens the first time? For the first time, we are unprotected. That's exactly it. In the first connection, the first time that we log on, there is a window of opportunity for an attacker. And that a weakness is known as trust on the first use, and it is based on that. Well, the first time we have to trust. We have to trust that it is good, and then an attacker could benefit from that trust on the first use, to carry out his attacks or just to do a manage the middle. And what happens when the mass age expires? Well, header has an expiry date, so to speak. So once that expires, we will be back to the same situation. We will be left unprotected once more. And this is what sometimes attackers use, well, to carry out, to implement their attacks. So what do we do? What is the security measure that has been implemented to prevent or to prevent being that exposed on the first time? For that, we have created a preload, that is to say, preload services. This started off from Chrome. The people from the Chrome browser, in their source code, they recorded they hard-coded a number of domains and said, I want to be protected from the first connection. I want the first connection to be the first connection to my domain to be a secure one. And sometimes the domain owners made requests to be included within that list so that they are protected from the first time. And now let us move on into greater detail for this our protocol HPKP. So let us take a look at a number of directives that can be used. Directives that help us specify the protocol. So the first one of the headers is pin SHA-266. 256, and this tells us the pins that are expected for a given domain. And well, as the name says, it includes, well, a hash function is applied, SHA-256, coded in base 64, that is applied to the subject public key information, which is a field in the domain. And in this case, in this way, that's the way the pin is calculated, is worked out. Those pins are sent out to the browser. The browser will store each of these pins for each of the domains. So we are telling it that this is what we expect. This is what is expected. So if we break down the RFC, it is recommended that we use at least 2 of the pins. So therefore, one of them is recommended to be contained in the chain of certificates, and the other one doesn't have to or doesn't need to be there. The other one is just as a backup. In case there is a failure, you can use it as a backup. So we move on with the directives. As I said before, we have the Message Directive. And as I said before, well, for you to kind of get a feel of it, it is kind of expiry date. That is to say, it is the time, the length of time the headers are in force or are valid. Once the expiry date is over, the headers are no longer valid. So that age is counted in number. So that is to say, the browser is told about the number of seconds to store pins. And this is important. Pablo will tell us more in demos. We can tell it to include the subdomains of a specific domain. But what happens if in our list we have the pin of a domain, but if we access the subdomains, we don't want the subdomains to be unprotected. And this directive allows us to include subdomains so that those subdomains are also protected. And last, we have the directive report URI, which is optional. And in case there is any error in verification, a post request would be sent to the URI that we would specify. In this manner, there will be a report as to what is happening so that remediation measures can be implemented. The recommendation here is that the URI to which we send the post should not be the same URI of the domain that is failing. Otherwise, it will not reach where we want it to reach. So we did some testing and we have detected cases where they say that post request is sent to the same domain. We should bear that in mind. That is a recommendation. So this if you want to use this protocol well, you have to use them well in this fashion. You want to use them well so that they fully protect us. So in this case, the recommendation is not to use the same URI, otherwise that post notification would never get to its destination. And this is a functionality that has been implemented after Chrome 46 version. So here on this chart, we can see an example because we are talking about max age, directives, pins. So just to make it more specific, I've brought this example with me. These are 3 different pins. And here we are specifying a max age. So this time this is the number of seconds in 6 months. We are saying that these headers, we want them to last for 6 months. After 6 months, the headers will no longer valid. And as we said before, we would be back again in first connection. And we are also saying that we'd like it to include the subdomains associated to those domains. And I guess that you are wondering, well, how can you consult those headers? Well, very easy. You just do curl. Pablo will help me out there. When we have a domain and we want to know whether it is using this protocol or not, we take a look at the headers. In case it's being used, the server has sent out the header HPKP, and then we do curl -- head, and we tell it that we want to take a look at the headers. Which ones? Facebook, yeah, or GitHub. Yes, GitHub. There are very many developers there. So this is the header, public key pins, where we included the max age, the pins of the certificates, and this time it also has instruction to include the subdomains. This one looks quite good. In this fashion, this is very simple way to do it. We can consult the different the headers of the various domains. I'm sure you are wondering, how do you work out the pin, how do you calculate it? Well, it is very, very important to mention that it is not calculated all over the certificate, but just with some of the fields. Actually, 2 fields are added: the subject public key and subject public key info. The result of adding these 2 chains, then you apply the SHA-256 function, and all that is encoded in base 64. And that's the way you calculate the pin for that domain. And that is the pin that is included in the directive SHA-256. And this raises an interesting debate. What would happen just in case the expiry date or any other field of the certificate will change. Well, the PIN of the certificate will not reflect that change because we have only applied it to those two fields. So therefore, I guess that there are very many security experts here. I don't know, what do you feel about the level of security provided by these protocols? So this shouldn't be necessarily always negative. Well, in some scenarios, this we could also be interested in not having the PIN changed. For instance, when it comes to renewing a certificate, in some cases, it could be that not reflecting the change could be advantageous. Well, we may debate that on the question and answer session. So to calculate the PIN, we have brought some examples with us. We can do that in several ways. So we brought with us the freak way to do it, and then we also brought an easier way to do it. We'll show the two of them to you, and then you just take the one that you like the most. So using the library of OpenSSL, so you can calculate the PIN. And with that command on the screen, you can calculate it. What we are doing right here, we are doing it for domain projects and DVL that comes from a university, and basically we are downloading the domain certificate. We can do that through OpenSSL. We get the public key of the certificate X509, then we change the format, and then we calculate the SHA-256, and then we encode it in base 64. If we use that library help us calculate the PIN for the certificate of that specific domain. It's a question of adding those commands to each other. So if you are not that fond of domains and consoles and dashboard, there is another way to do it, a simpler way to do it, yeah, which is also a more graphical way to do it. So in this case, we use a calculator. It's available on the internet. You can use it to calculate the PIN. And now, an example of it. Okay, we'll go to GitHub. So an example with it, so we go to GitHub, and the first thing that we will do is to download the certificates. We export the certificate, full chain, and then in pen format. Well, this is the format that our calculator needs. Okay, we store the certificates. So this starts with begin certificate. Down to the end, we copy the chain. So we have a different pin for each begin, because we have this is the certificate chain for GitHub. Google is always helping us. This is as simple as to paste the certificate there. So you only need a couple of clicks. So we get all the certificates here. And here, right at the end, we have the pins for the GitHub domain. So they look so strange because, as I told you, that they are encoded in base64 applied over a hash 256 function. Now that we have the pins for that domain, that's the domain that we want to access, and we will check whether they coincide, whether they match those that we have stored. For that, we are going to use the tool pin patrol, which is available for both Chrome and Firefox, and that has been designed by our colleagues at Telefonica. They have done a great job, and this pin patrol tool is really helpful. We'll tell you more in detail about it. But for the time being, we'll show you this example. So in this case, we'll go to GitHub, and now we see that it is using HPKP. So it will be valid until the 29th of January. And here we have the pins for GitHub. What are we going to do? We are going to check them against those that are stored. We said that at least one of them should match those that are stored. At RM1, we go back to our calculator. Alright, here it is. And actually it also, the one that is after that one is also there, the WOI. We would also have it there. So this time there is matching of two pins. Therefore, it is included in there. This tells us that the protocol is rightly used. The pinning of the certificate matches those of the certificates stored, and this tells us that we are protected, and so this is a simple example of how to calculate pin number. So I understand that many of you are wondering how you can implement that in the server. This is very simple to do. We have brought some examples with us for different web servers, and you only have to include a line saying that you want to use different headers with different directives. Now that we will take a look at different cases. In the case of Apache, as I said, it is just a question of adding it to the setting of the server. For that, you have to enable the header modification. You have to include the header. It says that you want to include the public key pins, and you have to specify those pins in SHA-256. And then in this case, you can tell it that you want to use the Segreg Directive so that they are valid over a given period of time. And then you are also telling it to include the subdomains. So for instance, in Nginx, here you would have to include these lines in the server, so it is including this line as well as the expected pins. For light TTPD, you have to do exactly the same thing. You insert the pins and you tell the tell the directive, the header that you wanted to use. And for the case of IIS, you would include this code on screen, also very simple code that includes the pins of SHA-256 with base 64 with the subdomains. So, well, the only thing you have to do is just to insert the line. That is enough. So it is not complicated. It's not difficult to include or to implement. Now, a few security considerations. After seeing all that, well, we can see that this really makes sense to use all these when we are using HTTPS. We are talking about chain of certification, certificates. So when we are working with HTTP, perhaps this doesn't really make much sense. However, in our research, we've seen that this is practice much more frequent than we thought. We've seen that in many domains, in many places, this type of protocols are being used under Protocol 80. So this is quite interesting. And actually, what is recommended is not to accept headers from HTTP because they may have been tampered with because this communication is not encrypted. Therefore, accepting it could be dangerous. And now we'd like to share with you, to tell you about shutdown. We'd like to share with you some of the cases and let us say the high number of cases that are doing this. So let me get this ready. Okay, in the meantime, to tell them more about shutdown. Well, I'm sure that you know shutdown. You know that shutdown allows you to look for, to search resources on the internet. But I wanted to tell you this, that when we search servers that are implementing these protocols, and well, they should be running under HTTPS and then the port 443. However, when we look for port 80, we see that there are thousands of servers that are in port 80. So we would like to call your attention to this type of practices because, as I said before, they can be dangerous. So this is the way we search them. We search by header, public key pins, and also port 80. So we had 1,103 results. These are the number of servers that are using this protocol under HTTP. That's an example. So SHA-256, this is a domain from the US. So many more also on the screen. This is a good fun exercise if you want to see it by yourselves. Germany, etc.
Bueno, sobre el HTTPS.
As for HTTPS, just the same. Actually, if you do the same here with HTTPS, you will get a larger amount of hits, servers that are locked, that have the HTTP, and that do have the header. So if there's something in between, since it's not encrypted, the header can be tampered with. So they can tamper with the duration, for example, or the length rather of the header in your browser. That is the one protecting you, leading you towards HTTPS, or verifying that the certification chain is valid. I'm afraid I cut into your presentation, but well, you see, there's been a change. Good. As we said, these protocols need to be implemented both on the server side and the browser side as well. So going deeper into the browser side, Let's see. It's been implemented into several browsers, but not all of them. There's a lot of work to be done here. As you see, Chrome implemented it from version 46.0. Point oh. Firefox 35, version 35, but preload sites that I mentioned before, these were added in version 32. As for Internet Explorer, it is not supported at all. And then mobile phones, well, this is funny, because we see this is the field where the least progress has been made, so it's a virgin territory that needs to be looked into. And Firefox Mobile version 35 onwards. But we've seen that for mobile browsers, this is where it is less protected and it's not so widely used. So let's move on to the browser implementation. We've referred to the server so far, but it is also necessary for browsers to support it to be compatible. We've focused mainly on the most used versions. This is Firefox and Chrome, and they implemented their own way, each of them. They have their own way of implementing protocols, even if with RFCC there are some recommendations that need to be followed, but yet there are some open items, not closed up, that each browser developer interpret in their own way. So we've gone deeper into research, how it is done for Firefox and Chrome, and this is what we wanted to bring here. For Firefox, if you follow this pathway for your user, where you've got your Firefox set up, you will find a folder, or a file rather, that it's a Site Security Service State. You open it up and you'll see that it looks quite unlegible. Let's refrain ourselves instead of saying that it's a bit even worse than that. That's where we keep all the information about pins and headers sent by the server. For those domains that have been visited by the user, the pins are stored there, and this is the way the browser can recall them and know the ones that need to be checked against. As I've said, for Firefox, there is a plain text table file with different fields, one of which specifies domain and protocol. Secondly, we have a score. This field here has as a starting value it would be 0. That's the starting value, and from there we increase it one by one for each successive day that the domain is visited, which means that if I go to GitHub today, so starting value is the 0, then one visit it goes up by 1, and tomorrow the score value will be 2. 30 visits tomorrow, so the value will still be 2. Just that it's 1 per day. So keep this idea in mind. It goes up 1 by each day that you visited, and the reference is the date and time, the current date and time of the system. This is significant, and we will see that later on. And so it goes up 1 by 1. The higher the score, then it means the more times this has been visited. So it has to do with browsing habits, right? To calculate this score value, there is a value on the third column that calculates the number of dates passed since the starting value to now. This is the reference value for date calculation in computers. You'll know that. And then we have a series of fields that are tabled by a semicolon. And we have time, which refers to what we mentioned before. That would be the time, the expiry time for headers. That is max H that I said before. This would be the expiry date. And besides that, there's state for Firefox. There's another value That is something they use internally. It's not been documented, and we don't really know what it is for, but it is clear that it has three different states: on, off, or overwritten rather. And you can also say if you want to include subdomains. And then we have the array of all the pins that refer to the domain and that are separated with an equal sign. So this is the pin jet, and this is the same, and this is the second. And that's the way Firefox has to recall and store the pins that are relating to those domains that have been visited. As I said, this is not very legible. I don't know if we have any examples here, but this is interesting, and I encourage you to go to your browsers and see the places you've visited and how it looks. And again, it's boring, not very legible, and not user-friendly at all. To sort it out, our friends at 11 Past came up with a wonderful idea, and they've produced an extension for Firefox and Chrome both that helps us and simplifies this visualization. At plain sight, we can see all the domains that have implemented set protocols, the features, the purposes. Let me show you the extension. It's just to go and say, I want to add the extension. That's as simple as that. And like this, you can see the domains visited by the user and that are using both the HTTPS and HPKP. So Pablo has it with him. What domain? Well, you choose. So this is it. So you see the domain, that's on the left side. That's GitHub with HSTS and HPKP. That's the score, the value we said before, number of days past where there's been a visited domain, the date, the expiration, expiry date, the security features that we mentioned, and then a bit more to the right for HPKP. Well, it indicates some subdomains inclusion as well, and then, as I said, on the right side, pins that are allocated to each of them. So as you can see, it's much more visual, much more practical, and that way we can gather all the information on the headers. This way, as I say, it's much more visual and straightforward. It makes life easier to us. We use it and it's great. And next, let's see how they've done it at Chrome. We've seen it for Firefox. Let's now move on to Chrome. Here, this would be a JSON file, contrary to Firefox that uses a plain text file. This is the pathway as well. That way you can see the file used by Chrome. And here, one of the main differences compared to Firefox would be that it does not include the domain directly, but there is a hash to the domain. This way, they wanted to make it a bit more difficult to know the domain, and in a way to keep it confidential. But as you can see and picture, there are ways to circumvent it, to go against or bypass the hash, which should not be easy to do because it's a hash, but there are ways to do it. Then there are some fields with similar indications as before: hash list and a certificate list, expiry date for the headers, and then there's this other value where the process would be forced to go through HTTPS. Apart from all that, we have the expiry date or expiration date for hashes, and if we want subdomains to be included or not, and then there is the time when the pins were observed, both for HPKP and HSTS. And just as a final comment, Chrome does have an internal interface you can use. You see the address on screen, and that helps us visualize and watch some interesting questions about this kind of protocols. And so this scene about HPKP, let's move on to HSTS. I give the floor to Pablo. So HTTP, strict transport security, and that's what HSTS stands for. And this is supported by most modern browsers. The idea is for your browser to remember that whenever you visit Facebook or your email or your different accounts, it needs to remember that even if you set the domain without saying whether it's HTTP or HTTPS, it needs to know that you need it to go through a secured connection. And that's when the servers, the first time around we create a secure connection to the server, sends us a header that is called strict transport security that the browser stores, and there's kind of a cache. And the next time we open it and we type outlook.com or whatever, the browser will first check the cache and then say, well, if I do have the domain in my cache and has a life, which is the max age, that it's long enough that it's not expired yet, I need to have 443 port, that's HTTPS. So we would not be vulnerable to this strict version 1, which was an attack from 2009. That's a strict SSL strip. Well, there's a problem there with the first connection, because when we go to the browser and we set it up, it might be that I type gmail.com, facebook.com, whatever, and my browser sends a request to the HTTP the first time because the cache is it's empty, right? So there is this preload concept, the same as with HPKP, just exactly the same, and we will mention that. This is what I said. So check out compatibility for Chrome. This is version 4, and it's been compatible ever since. Firefox version 4, Explorer, Internet Explorer since version 11. That's compatibility with HTS. And so they were lagging behind compared to others. Opera, that's version 12. Safari, that's version 7. What about mobiles? Well, it changes a bit. If you see Chrome version 18, Firefox 4, Internet Explorer mobile not supported, and at least when we recorded it, it might have changed. And Safari version 8.4, not so long ago. 8.4, not so long ago. So what does it mean? The minute browsers support HSTS, there's a technique that is number 1, the strict transport version, that stops working. And why is that? Because of the headers themselves. It is true that you could intercept the headers, but the minute there is a secured connection on the browser, we have a secure channel. It will be read by the browser, stored on the cache, and all connections afterwards will go through HTTPS and never HTTP. So it doesn't work. That strip won't work anymore. So let's see this HSTS header. So this is a header written Facebook and goes through HTTPS saying max age and around 15 million, I don't know how many seconds. So the minute your browser gets the header and processes it and stores the value, these 15 million plus seconds, that's the time that the header value will stay on your browser, which means the next time you go to Facebook, facebook.com, that's what you type, and there will be no HTTP request, but it will check expiry date, which of course needs to be translated into date. You can go into Google and Google 15,552,000 seconds, translate it into months or days, and Google can do it for you. And same for the PIN patrol, and it expires within 3 months, 1 year. It is funny how if you check out Twitter, it is funny. And here you have preload, right? For Facebook, and indicates that it's been preloaded for the first connection. So 63 million. So over 631 million. So 30 years or so. So for the next 20 years, whenever you type twitter.com, your browser will not ever send the query or request through HTTP, but the query or request will go through HTTPS ://. This would finish when the user says HTTPS ://. But how many of you type that? Well, there's always one raising their hands, but well, most people, that's true, especially as technicians, that we understand problems. What matters here is people outside the room. 99% of those people using new technologies that are out there are not the ones that need protection. That is companies, that is users. These people usually will say gmail.com, twitter.com, and that's it. So that was the problem, the first login, the first connection. So Twitter, 20 years, funny, right? That's the time that the value stays in cache. The longest, I think, the longest, yes. So you can have a time attack, and we will see that later on, but everything will expire. Certificates and warnings will come up from everything if we go so far in. So this is what I said before. This is the first request problem. When we send the first request and we enter a domain once again, your browser sends this request to port 80 by default, this SS strip technique that I mentioned before. This is from 2009, but there is a second version from 2014. And what it says is that with a man in the middle, when requesting the first time around, the HTTP request, we could trick the client, so all the communication, even if redirected to HTTPS, the communication would be with HTTP for the machine in between, and the machine in between would communicate through HTTPS. That's good. That's good. But it's a problem that we could even have with HSTS. Not with technique strip version 1, but strip version 2. But because version 2, what it does is it deletes those HSTS headers. So I can log into Outlook or Gmail, and there will be someone in between. But the minute that I get a secure connection formalized on the other end and I get the headers, I will delete them. So they will never make it to the redirection. Sorry, the headers, the redirection will never make it to whoever's requesting the domain. So in that way, we can make sure that the headers will never make it to the client. We will see it in practical terms later on. And that's the best way to understand it. For which we will be using that strip plus connected in the same way. It was developed by a researcher called Leonard Dumbe, and it's been implemented inside the man-in-the-middle framework, which is quite a modern tool using modern network attacks, which we recommend you to try them out. The attack that we will try will be on a Windows 7 machine. Firefox, that is up to date. Let's try it. Before we try it, check this out. Here it is. The target would be this, precisely. This is the login. This is an Outlook account. And this is the password. And now, when fun starts, I love seeing Pablo in action, especially when it doesn't work, right? This is a summary, right, of what we've just said. So let's start a machine. So first thing, if you've never seen it, it could be, let's try a man-in-the-middle attack using spoofing techniques. If you've done it with .cap or other tools, or better cap, with any of those tools, you'll see with this kind of modern tools, it's pretty simple because it's a spoofing attack that I want. I want to ARP it as part of the spoofing thing, and that's the target. This would be Windows 7 machine. I think this is the IP. And we do want it on the router, so that's against the router. Yes, I mistyped it. So it starts now. We check the ARP cache. And we should see that the physical address 4.1 equals .5. So let me highlight it. You see 5 and 1 have the same physical address. What does it mean? Well, Windows 7 now, when it wants to send something over the internet, it sends its first thinking that that's the physical address of the router, but that's what we get. This is the Kali machine. So we are in between the communication. It's so very difficult, as you said, and it's always been so different, so easy to get in the middle. And on top of it, let me see if I can go back to Kali. Stop this. And let's add this option. We set up DNS, we spoof it, and this HSTS module, it opens straight plus plain. It is implemented on the tool and it's on already. And so here we have is a DNS, and that way we play around, as Carmen said, with include subdomains. Google.com, for example, does not include subdomains. the strict transport security does not include subdomains. This is good. They realize this is something good. For the researcher, for the attacker, that's good because, for example, if you go into Gmail, it's just an address, and you end up in accounts.google.com. So if there is no strict transport security, so HSTS header part, if there is no protection underneath in every subdomain, there might be a reason why they cannot do it. And so you could use it, and when there's a request to google.com without a header, that you could spoof them and say you need to connect to account.google.com. Real one is account. When you do this exercise, you will see that through DNS there is this technique where it seems that you're getting connected to valid domains, but they do not exist. But they're valid for this strict plus SSL strict plus attack because there's nothing on top of it. So those invented domains are outside the reach of HSTS. If I were to link through Twitter or elsewhere and I was in between the communication with the attack and I would send you a link aiming at account.google.com, if we had HSTS from google.com downwards, even including subdomains directive, you would be protected because that account.google.com would go through HTTPS. But if you don't have it on upper level, if I move from account.google.com and in between the communication and I can spoof you, I can take you back to the site that I want you to without the HTTPS. So fingers crossed, Carmen. You see, DNS, SSS strip. Here it is. Leonardo. So, check that it is true, that we've been poisoned, it seems so. And let's open our Firefox app, our BIM patrol. Let's try Google out. What happened here? HTTPS, and why is that? Because HSTS is on cache already. When you have it back to account.google.com, we saw on PIM Patrol that we did have the header for the domain, which means that here there's a problem. This is that we are bypassing SSL strip 2. This partial bypass, and so if the header is there on the browser, we are in trouble because that means we cannot trick it. We cannot trick the user. And this is a problem from the point of view of our auditing, of course. For security is all fine, but then on the other side, so check this out. This gone a bit crazy now. See, it's zapped. What happened then? When you log onto Outlook, I don't know if you use it, but we've chosen it as a victim. Not cached, we logged in before, and yes, it's true. There is no HTTPS. You type outlook.com, there are some redirectioning, and then some of those domains do have HSTS, and so if you were logged already, that's where we would be. But that's not the case. That is strip 2, which is working. It is working nicely. And so, if we come all the way here and we say log in, oh, they've changed the main site, the home site, right? They just changed the day right before we test it again. So we still go through HTTPS, TTP. So it's not secured. And you see, these messages, these warnings are more and more aggressive, but this is good. You need to know that it's not a secured connection. And I guess January 1st, 2017, they will be even more aggressive when you log in through HTTP or you type your credentials on HTTP. Carmen, your Outlook, your account. Worst thing is not the account, but the password, I'm afraid. Imagine if you had that account. So, what's happening here? Here, this bulk. Oh, it's gonna be fun. So much fun. So let's see if you can find it. See, it's not even small print. It's just the next step. Way too difficult, right? So you all know my password by now. And that's user and password. Username and password. That's a strip 2. So, that's nice. But it's only partial bypassing. So, we need to fulfill a few conditions. There's a prerequisite. And that had to be cached already, right? I've been talking to Jose Selvi, who's in Leon. Well, I was on Twitter as Carmen was speaking, and we forgot something. It is true, we said that for Shodan, we could have HTTP and have servers that send headers on HTTP, but we did not refer to the browser behavior. That's when the browser will say no HTTP. But it also depends on the implementation. It's a research, and Sergio's work on it as well. And he said, well, the browser will say max H. Well, the other way around. Skip the message because it's on HTTP and should be like that. If there is a header like that for HPPK or HSTS, it should be ruled out. But what's funny is that there are servers that are sending the headers. You say the header does not remove them. So that's what Shelby said, that those headers are not accepted. And about Salvi, he is a Spanish researcher, quite well known, good papers, and he was playing around with HSTS, and he has this idea. What if max H expires? How does the browser behave then? HTTP request once again, port 80 again, if we do not type in the protocol into the address bar. So his hypothesis or scenario, well, he developed it. What if I try this? What if I try this? It is all about trying and try to understand it. So he realized that if we change the time on the device, the HSTS entries expired. That makes sense because they come with an expiry date. So he came up with an idea. What can I do so that devices move the hour up or down? How can I do for those to move the time up? And how do they work? We have Linux machines. We have time synchronization. We have macros as well. And it was funny or different. He has DeLorean. This is a tool, which is an NTP server, which when you request a time synchronization request, it just changes it. It changes the reply. The minute you intercept, since you are in the middle of the communication, you can see there is a request and take the machine to a different time stamp. This is interesting. So the idea is the following. We have ARP spoofing, SSL strip 2, and then the Larian, which is an NTP server. We have an IP table standard or rule to redirect UDP requests to port 123, and we can change them, and we can change time on the machine. Question is, when do they synchronize time?
So the theory is okay. However, the problem here is studying how, or rather when, machines make that request. So it is more complex than it looks like. It is true to say that users can change the time, and Windows system. In Windows, if we try to move the time more than 15 hours forward, then the machine resets the time, goes back to the original time. So how many of you use Linux? Oh, very many. And Windows? All right, so there's a bit of everything. Good to see that. So in the case of Linux, we tried with Ubuntu. So he did tests. He could see that the moment the machine went online, the machine did a request for time synchronization. It is very interesting in this environment. So imagine that someone could also disable your Wi-Fi network. You are on a private network at home, and then you are the authentication attack is launched to the points of access. Then you connect again, you go online again, and you are waiting in the network to modify time. So if you have any questions later on, we can discuss it in the question and answer session. So this tool looks very nice. It looks like a Ferrari car, isn't it? So cool. Notice the message by default. This is trying to take us 4 years forward in time. So you can change and say, no, I just don't want to bring it 4 years forward because there will be alarms alarms will be triggered. I want to make it to be more silent. So you may go and say, well, 3 months is okay. Try not to put the time very much forward so that you don't create lots of noise. If you move it forward too much, that will create or may create problems in the actual machine. So now, comment, fingers crossed. Now Ubuntu, even smaller this one. Can you see it? Okay, we will enlarge the screen now. Yeah, I cannot read it. Okay, I'm enlarging it for me, not for you. This is poisoned. We leave Windows and see in this machine. This is quite idle, not too much activity here. And now poisoning target is Ubuntu machine. Oh, I can find it. Oh, here it is. poisoning, see if it went successful. These two have the same value. So the machine thinks that this is the physical address of the router, which is actually ours. So we open the browser. Looks good. Also pin patrol. We want to open that. Date also important. 3rd December 2016. So first of all, we'll take a look at Facebook domain. Facebook.com. So in HSTS we cannot do spoofing here. Okay, date 31st May 2017. What happens? Why couldn't we do it? Facebook.com, yes, but we spoofed it and we are redirecting it to this subdomain. Does this subdomain exist? Does it ring a bell to you? Have you seen it before? Yes or no? Have you? Well, I hope someone says yes. No. If someone says yes, this does not exist. If we type in whatever here, because it goes through HTTP. So Gmail is not in the cache either, so therefore the attack is not successful. Account.google.com, does it exist? No. Does google.com has HSTS? Yes, it does, but are subdomains included? No, and they are not. Even if we request the domain, it is not being protected because I am spoofing it through my account.com. That's what explains it. That's what happens. We try this one, we will cache this one here. This is with HSTS. If we wanted to trick the browser again, we will take it to a future time. So we use DeLorean. Let me say something. The date used is the day of the system. To see when the headers expires or not, it calculates the days that have gone by, taking into account the date of the system. Pablo will change the date of the system, will take it to the future, will make it expire, and in that fashion it will bypass it. So this rule, well, we would have like 3 rules. If we take a look at IP table, we will find 3 rules. One for the one that we have just included, one for the 123, and the other one for the 10,000 ports. That is to say that this the strip, that's the man in the middle that says puts it automatically. Man in the middle framework put it when we run the tool. Then in the background it touches everything that needs to touch in the system so that all the plugins work. And this last entry, we just enter it by hand, and we are telling it the following. We are saying that when machine, before it does any routing, if it gets VIP traffic, any origin address, any destination address, destination port 123 says redirect to port 123. And what do we have in 123 port? We have the DeLorean tool there to spoof the response, ready to spoof the response. Well, it is has been changed a bit on Waka. So as I said before, we can simulate what would happen if someone would take us out of the network. So the victim has a Linux system, we are on the same network, and if it is logged on to a Wi-Fi, we try to go out of the Wi-Fi to reconnect to get a different IP address. Once it is again in the network, the machine will synchronize. We'll ask it to the IP address. Okay, we'll simulate that now. So now, fingers crossed. So something is happening there. So the good thing is that to open a Wireshark, to filter it through HTTP and see what happens at a lower level. We have taken it to the future. There says going to the future, 2020. See if everything went well. 2020. 3rd October 2020. Calendar. Well, the calendar hasn't changed. Oh, yeah. Has it changed? Oh, yes, the calendar has changed. Well, getting there. Okay, here we go. It took a few seconds to refresh. Now we are in the future, and now the entries are no longer valid. They have expired. Okay, now it has taken us to account again, HTTP, Carmen's email address. Well, this is more difficult, isn't it? I think it should be somewhere here, right at the bottom. Here it is. Okay, very last line. That machine, HSDS entries that are expired, not the Twitter ones, and you are telling it to move 20 years ahead in time. This is very complicated because it will trigger many alarms. So I hope you understood that well. So now a few conclusions before we finish. And conclusions. This is not a widespread implementation, so it is often found in the services that you use on daily basis, but however, in highly critical environments such as banking sector, they have not implemented it. But in services such as Facebook, Amazon, Outlook, Gmail, it is already implemented. It is true that some of them has HPKP and HSTS, both of them. HPKP is less implemented or less widespread. It actually makes sense because HPKP is came out later in time and it is also more complex in terms of pins, etc. So therefore we see significant differences from we've seen that in the research that we did. HPKP is not as widespread as HSTS, but at the same time there is a good reason for it. Not using them with HTTP port makes sense, but I don't know whether all of you, but most of the ports will not take into account those things that they get through HTTP. And then using preload and include subdomains. In this case, Google is right for that. And with regard to browsers, some of them do not support these headers. They are more and more, these headers are more and more supported, especially HSTS, but some browsers have taken a long time to support these protocols, and especially in the mobile environments. Mobile environments implement these protocols much less. So they are prone to receiving attacks and to having vulnerabilities, weaknesses. The more they are used, the more they are implemented, more people will look into them, will find vulnerabilities, and will eventually make them stronger. So that's the idea about it. So we want the protection mechanisms to become more and more robust to protect us all. And well, that's about it. That's all from us. Would you like to add anything, Carmen? Yes, I would like to say that one of the purposes and objectives of this talk was not only to get to know us, but for you to have a feel as to the importance of these protocols, what they are used for, and it is not a question of us trying to foster the use of them, but for them to be used properly. That is to say that there are no mistakes made in terms of the configuration and setting up process, because sometimes we believe that because we are using the specific protocol you are more secure, but this is not the way it goes unless you use it properly, you set it up properly. So bear that in mind, so you are not unprotected when you believe that you are protected. I hope that everything has been clear to you, that you are more familiar with them now. And those of you who were not aware of them and those who knew them before, well, I hope that you have enjoyed our presentation and all the attacks that Pablo has shown you. And if you have any questions, we will be very happy to take them. Thank you very much for your attention.
Sí, buenas tardes. Muchas gracias por las charlas.
Thank you very much for your presentation. Very interesting. Well, HPKP, do you use it for, can you use it for denial of service? Actually, the machines that are on port 80 that has HTTP, are they compromised? Could anyone introduce HPKP there or not? Well, with regard to HPKP, it is not recommended that you use it on port 80, and that's why you need to set it up properly. It is true that if none of the pins matches, I told you that one of them, at least one of them, should match the pin stored. Otherwise, there will be a denial to the service, and this is what everyone wants to avoid: denial of service. Therefore, we have to have the knowledge. You have to fine tune and be very careful as to how you use it and the pins that are included. So you may remember that I didn't ask you to check each and every one of the certificates in the chain. That would be much more demanding in terms of security. However, we don't do it in that fashion just to prevent this type of problems, this type of problems that I have just mentioned. That's where the knowledge or expertise of the experts comes into place to see to what extent yes, to what extent no. It is true that HPKP is slightly more complex than HSDS. Thank you very much. Any other questions? First of all, thank you very much to the two of you for the workshop. And in Windows environment, for DeLorean attack, when does it actually synchronize Windows environment? Whenever it is, whenever it gets started? Well, I have that very same doubt, actually. Well, we have Jose there. He can give us a hand. I think that it is around 7 days. 7 days approx. So perhaps it is best to ask Jose, because Jose has looked into it. So it should be around 7 days, or perhaps it is more chaotic than that, is longer than that. But it is not every time the machine is started, every time you log on to the internet. So the good thing about Linux is that from the viewpoint of the attacker, when you log on to the network, Ubuntu will make that request, but not in the case of Windows. The problem with Windows is that even if you change that time manually, if the change is very big, it will go back to normal. It will reset itself. It is complicated. It is difficult. If you ask us about the Active Directory, this becomes even more complicated, more complex. Yes, that was yes, I was hinting at that with my question. Yes, it depends on the system that you analyze. So Windows, it is the hardest to push and to make it change the time. Okay, Windows is the most difficult in that regard. So thank you very much. So let us say that a final solution would be to save 100,000 million years of refreshment. Well, at the end of the day, it's a question of finding a balance between security and usability. So you may have a very secure company. Well, this is a bit of a discretion, but I would go back. So you can have the safest or most secure company in the world. If you cannot make business, you would end up closing down your company. So what I mean is that we may try to strengthen everything to the utmost, as much as everything remains, as long as usability is kept. So it is important that we all understand it. So the business of security is about protecting the assets of the company so that the company can go ahead with the business. So in the case of Twitter, I think this is they have a good policy when they go and say, okay, 20 million seconds or 20 years, 20 years. That's it. You are ensuring, or what you said, that every time you make a request, it will go through HSDS. Therefore, you are ensuring that you will not suffering any SSL strip in my domain. Well, unless tomorrow there is a new vulnerability to change keys or whatever, and then another vulnerability shows up somewhere else. Is that a correct policy? Well, at the end of the day, he's trying to apply to implement necessary layers to have an acceptable level of security. Twitter's policy is a good policy to my mind, but perhaps it is a bit over the top. And actually, after a year, it will refresh that header and it will add 20 more years. So therefore, making it 21. Every time they send out the header, you are updating your max age. So for instance, if tomorrow you make a request to Twitter, then it updates in HSTS and then it says 20 years, it becomes 20 years plus 1 day. Well, perhaps in 20 years' time, the Twitter is no longer there. Who knows? As we said before, we recommend following the recommendations because sometimes these protocols are not used and recommendations for them are not followed. That is to say, use them with common sense. And then security is like a race between cat and the mouse. They are chasing each other all the time. So that's what we are facing. And same as everything in life, you have to get to know it as best as possible and try and fix problems all the time. So I believe that this is an interesting topic. This is an interesting field. Hello, good afternoon. Drawing on previous question. Any negative impact in extending that life cycle a lot? No, to my mind, no. Well, if you go and say 100,000 years, well, it's a question of finding a balance. Imagine that the domain cannot be accessed for whatever reason through HTTPS. If that is not possible, you would not be able to access the domain. Sometimes it happens. Domains that don't let you access through 443, through HTTPS, they just do not implement it for that very same reason. So in case there is any incompatibility or in case there would be any situation through which you cannot access through HTTPS, you are kind of blocking the access because you are saying that it is forcing you to connect in a secure manner. So it's a question of finding a balance there. Well, the internet, the idea is that we all move on to connections HSTS. And I don't know whether you heard recently from Apple. They included the ATS for iOS developers. They are forcing all the apps to consult through HTS. So therefore, all the internet connections should go through HTTPS. And then as from the 1st of January, the App Store apps, if they do not connect through HTTPS, the communication will not work. This is quite restrictive. This is quite a restrictive policy from Apple. So it is not that they have said it yesterday and they will implement it tomorrow. They've been saying it for quite some time. ATS was released in iOS S9 and they are trying to move all the communications through HSTS. So as Carmen said, if you set it, make it a year and you refresh it, so it is hard for you to not to use the service again in a year. So the moment you go there, the cache is updated and then the max age becomes extended. So the idea is that everyone goes to HTTPS and then to have encrypted communication, and then companies such as Apple are demanding for communications to be encrypted. Hello? Question. If you have a long-term certificate and for whatever reason you shut down the domain and someone else uses that domain, would that certificate continue to be valid in the computers where it is implemented? Well, okay, I repeat. I don't know, long-term certificate, Twitter, 20 years. Okay, so I close down my domain? Okay, I rephrase it. I go back. So if you close down the domain and someone else, a different person uses that domain, could you continue to access through HTTPS, or the certificate expires, even if you have the HSTS. Sorry, I cannot understand your question. Yes, I got it. So what he says is that you have a domain. The domain is shut down. Okay, tell me if I understood you well. And then someone else opens it again. Same name, different certificate. And he says, okay, because the domain is already cached, what will happen in that case? Okay, now I get it. You can always delete, but as we said before, yes, you can delete it. You, as the owner of the browser, you can go to the file that comments told you, just delete it, and that's it. Full of the story. So it is a text file that you have in your local computer. You can change it if you want. Yes, but not all the users will know about that file and will delete it. That's a very good question, actually. Yeah, it has to do with domain policy. Yes, it is related to the policy for domains. Yes, there may be a problem there, but the company that can open that domain, they should be reported about that, and so that they can clean or debug the cache. Yes, that problem may happen. Yes, you're right. Thank you very much. Thanks to you. And what happens if we are talking about the different certificates, different public key, and pins will also be different? Yes, but if the domain name remains the same, yes, you're right. You said that you can delete the file if for whatever reason that file were to be deleted intentionally. Could they have access to all the domains? Yes, they could. With the exception of the preload, yes. So at the end of the day, that is stored somewhere. You have it protected because you are the user and you have protected it with your permissions. But if you eliminate any command line for whatever reason, you can test it yourself. For instance, Gmail, you attack it, then you delete the entry in the file, then you restart the browser, and therefore it will be left vulnerable to that first request unless it is preloaded. That's what we said about the importance of the preloaded. There will be a strip when you are unprotected, but the moment the user access to that domain, then that domain would be included in the file. But as I said, there will be a window of opportunity there for an attacker. But I mean, if they are on your equipment and every time you start the computer, they modify the line. Oh, you're saying type of malware? So that was plain text. What about Chrome? Yes, as long as it is run with those permits, and as long as it would, it would upload the files every time you restart the computer. Yes, that could happen. Hello. Going back to the scenario or certificate from a different domain, and in this case, and this is just an assumption, would that scenario be valid provided the certification entity is the same? So if the certificate that has been issued for that domain is issued later on, for instance, I don't know, let's encrypt. That scenario could be possible, but that's what the certificate chain is for. That would be the ideal scenario. But if for any reason any certification entity does the same, that certificate will no longer be valid because the chain would be different. Okay, drawing on the previous question, or relating it to the previous question. If we are talking about a new certificate, the public key would be different, and if the field for which you have the pin, the public key pin, you concatenate them, and then you do the SHA 256 base 64. If those fields change, the PIN would be different, and then in the case of HPKP, pins will be different. However, they were saying that in the case of HSTS, where there are no pins, if the name of the domain coincides is the same, there could be a problem. Yes, but he's talking about certificates. Yeah, you are right. Yes, that's the way. That's a different certificate because those fields are changed. PIN would be different and it wouldn't match. It would not. Yes, because public key. Yeah, provided that the certificate is issued by the same certifying agent, okay? Because the public key is the same. Yes, it's the same. All right, thank you very much. All right, if there are no more questions, thank you very much for your attention.